you. Today's talk is actually going to be a little more general than just on mini computers. It turns out that to understand mini computers, you really ought to look at technology as a whole, plus the process that generates computers in the first place. And then I think then the whole business of mini computers and microcomputers and MIDI and MAXI and whatever, however you want to categorize them, makes more sense. So I have a number of slides that kind of get at these points. If you start with the basic process here, I hope we can get the whole process on the board, but well, can't quite get the whole process on the board. That what happens computers are mainly, or the whole design process, or the whole process of the computer industry is highly driven by the components, namely what you can build with. So you start with a basic technology, and of course there's other parts that feed the basic technology prior to this stage. But you've got a stage here of that seems to be emitting technology at a certain rate. Semiconductors, for example. That's one part of the technology that goes into computers, and it turns out to be a very large part of the technologies. From that, we go into something which very often is called architecture, which is really the design of the basic systems on which programs run. That feeds the process that creates systems programs. In turn, user programs are generated on that basic system, and then finally, the part that is left off is that the poor user is at the end of this high gain amplifier, or the user, I think, thinks of it as a very low gain system. And the other thing, that to get any changes, this is a very, very long feedback path from a user back to that technology, and it has to go through a lot of these stages. So we have people here who call themselves architects, and they are emitting designs like Fury, and at least the user feels like they know nothing about what about the final problems that actually get run on those machines. And it really is quite a problem to make this system work in a stable way in which you do get this coupling. And in fact, what we like to do is, anyone who professes to be an architect, we try to insist that they've have solved significant problems on a machine. That is, they're very good at programming, and secondly, they've really had to construct big programs. And to a certain extent, that's true right now. All of the people who are doing this kind of design have had a fair amount of programming experience. So this is a sort of the whole basic process, and if you look at that thing, that whole process, the delay through there is something on the order of 2 or 3. Well, it's probably longer than that, the order of 4 or 5 years. A new machine here is in the order of 1.5 to 2.5 years. Assuming you run this in parallel, that lags there, and you add another year maybe, so you're talking sort of 3.5 years through that, three years through that. By the time you get users on there, you're maybe another year, and that whole thing cycles in like 5 years. The PDP-11 right now is only about 5 years old, and it's just getting to the point where computing on it is not a pain. That is, it's software stable enough, there's enough of a library there so that you don't feel like you're inventing the wheel every time you start solving a problem. And high-level languages help this a little bit, so you can be buffered to that and that. So if you start out in BASIC, say in using BASIC or Focal or something other than an assembly language, you can bypass a lot of this this junk. Now, if you look at, I also like to look at machines in terms of machine generations, in terms of how they came about over time. And we started here with, I'll call this the one-person effort, in which you look at people like Leibniz and Babbage, Zuss, and von Neumann, whose names were, single people were associated with the machine evolution, and that was all a mechanical technology. And they were all of these designs, Babbage has once quoted that his sort of famous quote about the technology was, he was doing some calculations. He said, "I wish to God these calculations were done by steam." And it turns out that that was right at the limit where steam wasn't even working quite yet. And we make the same mistake that Babbage does all the time, too. The time he said it, railroads hadn't quite come in yet, but it looked like they were going to happen. And so he was working right at the limit of the technology. And he was totally a failure as far as a machine designer is concerned, even though he had the ideas and he constructed machines, or he constructed parts of machines. It never really worked because he was working right at the limit of what he could build. And so his main contributions turned out to be in other things, like the whole business of machining good mechanical parts. He worked at the limit and really worked on the whole machine tool industry, and a lot of his work made that possible. Anyway, machines were sort of forgotten for quite some time, and the next time one heard about them, there was a whole era here of electromechanical technology, of the punch card and all that sort of thing. But the computer per se came in the sort of electromechanical and vacuum tube era, where you were dealing with small laboratories. You still had one person that was associated with those usually, but there were really labs, centers, Cambridge, University of Cambridge, England, Harvard, Bell Labs were all places that were really doing work on these small computers. These were relays usually, and then they moved into vacuum tubes in the early 40s and during the war. And so the war actually acted as an impetus to build that technology, because people had to compute firing tables. So the wars are quite useful as far as technology is concerned, and the military is too in that regard, in terms of pushing for technology, because some things integrated circuits wouldn't have started in the way they did without the pressure on space. And this fed into a transistor technology, and here you had people's, again, Zuss and Eckert-Mauchly, and this was really, whereas this was one person doing something, this was a lab doing it, you had low volume production here. Every machine was sort of an entity into itself. And then we moved into what I think right now we're sitting in a medium production environment, in which we're building out of integrated circuits. That there's still a great deal of hand fabrication. And now finally we're moving into we're quasi into a fourth generation, which is a higher level of integration, in which you really are making machines in volume production, and these are the sort of Intel Intel sort of typical of that, where the semiconductor is a dominant part of the machine, and that becomes the well, in fact, the way I think of the semiconductor industry is there's the only thing that's with that much intelligence that can be built with that much intelligence but with less process control is human beings. That we're talking about really very high chip densities, very high memory densities, and of course memory is the dominant part that leads to the machine. A machine is memory, and that's so that the pressure there is to make the cost and ease of that very easy to make. Now, so if you put this in a time, I don't know whether you could, yeah, I think you can see it. I don't think the camera can very well, but this, if you kind of put this in a couple of time scales, here you had nothing much happening. This is 1600 to 1930, and there were lots of things that were important about that. So there was the vacuum tube, the electromagnet, and the telegraph, and then you had a whole bunch of punch cards and mechanical calculators. But starting in like 30 to 40, there was these electromechanical punch card kinds of things. I'm going to tune that up a bit. And you get something like the IBM multiplying calculator in like about 30. Columbia University was doing some work here with IBM, and IBM also funded some of the Harvard MARC machines, which are electromechanical. And then you get in, and Bell Labs was doing various kinds of work. So here you get this mechanical technology going up to like 45, vacuum tubes going to like 58, transistors, core memory going to somewhere in the 66s, around 66, and then integrated circuits and core memory and large-scale integration going up to in the time scale now. And the technologies are therefore marked by these big changes in, or the generations are marked by big changes in technology. Now, so my picture of what happens is that your things are dominated by technology. And now let's look at how we do relative to the car. So let's look here. The way you measure, or a good way to measure technology, a way that's a very common way of measuring technology, is on the basis of some technological indicator and as a function of the number of units that you build. So we're sitting here, we've built about 100,000 units, and we now have an indicator here. The indicator is really a product. This doesn't happen to be my indicator. This was done by a person at the MIT Sloan School, an economist. And his indicator is a product, which is really memory size times bits per second, or memory size times 1 over the access, in effect, the access time. So it's really a product of two indicators. So you have to bear in mind that this is going to give you a bigger number of change than at least I think we deserve. He did this, and you get a function that looks like that. That the technology of the ith unit you built is equal to some constant times I to the 2.5 power. Well, that's a big number. I mean, if you make I very large, say even I squared, that turns out that's like power. That as I increases, and your technology is going up very, very rapidly. So what's happened is over the range he measured, it varied from 10 to the 7th to 10 to the 17th. So our indicator has a factor of over this range is 10 to the 10th. That's a massive number, at least in terms of changes. And maybe you should ask, why were you so stupid in the very beginning, and so that this isn't so big? And it turns out it's been a hard fight all the way along to drive it up that axis. If you go back and look at the Harvard marks, they were really pushing to get that, and now we push to get these numbers too. So we're sitting here with some big function, some very rapid growth function. Now, let's contrast that with the automobile, just to give you some perspective. Now, the automobile is sitting here. The indicator that he used on that was, in fact, horsepower, a good technological indicator. It's had a range of 10 to the 8th, or about 100 million have been built at the time he did this. And this is varied like 20 to 200, only a factor of 10 over the life of the car. And in fact, it looks like that's now going to drop back. So his indicator is all really going to go to hell. He's going to have to get a new indicator, was what it amounts to, or he's going to find that the technology function is in fact negative on that, which is something I think we've all suspected for a long time. And that during this one big push, where there was in fact low horsepower, that was only at 0.1, and that's what it feels like it ought to be reasonable for a car. There's, after you've got about 4 wheels on it, there isn't a hell of a lot you can do in terms of, except make them cheaper or smaller. And this was during that sort of early mid-50s horsepower race in which there was this drive to get big horsepower engines in, and they had this big spurt and actually got that exponent up near 1. But that, I think, is clearly going to come down. So that's a perspective that we've changed in the order of 10 to the 10th, and the automobile may be a factor of 10, but not clear. So the model I want is that you've got this sort of thing, this technology generator that we sometimes think of as a cornucopia blasting out technology forever, and you take it and make the best thing you can at that time. There are actually 3 ways that you can observe how that technology has been used. First, there's the way that leads to the minicomputer. You take that new technology, which is an improved cost performance technology. You take that, you take as little of it as you can, you hold the performance constant or even decreasing performance, and you make the least size computer that you can make at that given instant. And that leads to what I call this minicomputer strategy. Therefore, in fact, the whole business of a microcomputer or a computer or processor, not a computer on a chip, but a processor on a chip exactly, is really this minicomputer philosophy. That is, you're taking the technology, and whatever that technology gives you, you make a computer of it. Because we've observed that a computer turns out to be about the best way to make a sequential circuit. It's a very efficient way to get control done, to control memory, what have you. Because it's mainly a memory-driven technology, but by putting this little fetch-execute cycle control logic around it, we find that it's a very, very powerful technique to build controllers. So in fact, with computers, you build controllers into every imaginable thing. There'll be computers in cars, computers in wheels, computers all over the car, in fact, based just because of the simple structure or the problem of control and the simple technique that a computer offers to do control. So that's kind of this new technology technology comes out of there, and you grab it, and you say, I'm going to make a computer with it, and you make the smallest one you can. And that's what I claim is the mini computer. You take this other strategy, which is pretty much IBM's strategy, and it looks like a substantial part of our own, which is that you assume that the person buying a computer has got a fixed amount of money to spend, or in fact a slightly increasing amount of money to spend depending on inflation, and that the computer goes into some kind of an environment, and that environment dictates the price that people are willing to spend for that computer. So in a large installation, the computer costs are becoming a smaller fraction of the total installation cost. In fact, it's now on the order of, the computer itself is on the order of 20 or 25% of the installation cost in a big installation. The rest is all programming, supplies, power, all of these things. And so with that strategy, it doesn't matter very much what the computer costs, because you've got this overhead. And with that, you take the technology that's coming out, you say, people want to spend $100,000 for a computer, and what they want is to be the most productive that they can for that amount of money. And you proceed to take that technology and squeeze it in this box until you get $100,000 worth, and say, well, that's your computer, because they're ready for that. You know, they're prepared to spend that, and in fact, it's the most economical thing to do in a fixed situation, because you're looking for more productivity in those environments rather than a slightly lower cost. You got this overhead, and it's not going to do you much good to reduce it to even zero at that point, because what you want to do is get more out of that system. And by putting more technology into that environment, you get a heck of a lot more out of that whole environment. So you take this technology to generate more compute power. The third thing that you can do is that you can build some, I'll build some interesting new structures that you couldn't have built before. And because the technology has changed, you've got higher density, you've got lower power, you've got higher performance, and given that, you can now build some things to do a better job that you couldn't have by what I'll call two evolutionary kinds of strategies. This one, you always uncover new applications. This doesn't really uncover any new applications very much. It's just sort of status quo, and you process more data with and not evolve very much. But here, you're really looking for new structures. And a couple that have been built is there's a CDC star and the University of LIAC 4. These have both been fairly unsuccessful as far as machines are concerned, but you could expect that maybe in 10 years these might be ways to compute, and they may be cost effective, and then in which case they'll get pushed up into being more of a standard structure. But they were predicated on having a good technology, and you couldn't even have considered these machines in 1960. Actually, they came out they started on them about 65, but they started too early, it turns out. Now it's fairly easy to build those, and again, it's this sort of recurring theme of trying to build too close to the limit of that technology. Now, if you look at, in fact, what the mini computers delivered, this sort of shows the way this function has operated. Let's see. Thank you. I think we're almost all on there. Here, again, we've got a log scale. This is starting at $100, going up to $100,000. So we've got 3 decades of price, and we're starting here at 1960 and going to 1974, 75. And about the first mini computer was a CDC 160, which came out in about 1960 at about $60,000. 12-bit machine. The PDP-5, which was sort of our first mini, was in '63 for about $23,000, excluding the teletype. The 8 came out $9,000 cheaper at about, well, this is actually a little high. It's 8. This one's been normalized. It should be down in around $15,000, and that was in like 1965. And what we've observed is this exponential price decline compounded at the rate of about 30% per year. So you start here, we're starting at 60 and going to 75 at a 35% price decline. I prefer to think of it as about as sometimes a factor of 41%. I like 41% because every 1.41 is the square root of 2, and so that means every 2 years things are going to be halved. So you can easily count. If you know the beauty of all these exponentials is if you know one point and a number, then you can get everything else. And to a first approximation, it's about right. If you make it a little lower rate, then it essentially takes 3 years to. More precisely, it really takes about 3 years to get that factor of 2. And that's kind of what we've done. So this line is the 12-bit computer line, and this is the various 8s, and here's a Honeywell 12-bitter, and they all have fallen on this line. And I guess, I don't know, the current going rate of a board-only, of some board-only machines is, I don't know, it's around, probably, it's less than $1,000, and I think it's 500 if you just get it's substantially less than that. These are the 4K 4,000 word memories. So this is with a given single configuration, 4,000 word memory configuration. Looking here at the 16-bit computer, then you find that it's shifted up, and there is a similar curve, and it's following the same cost reduction. So either you look at the prices here, you can say the 16-bit prices are delayed by either by about 2 years, or they're shifted up here by about 30%. So this is really the mini computer, and this is this philosophy of taking the given technology, making the smallest machine you could make at that time. In fact, I remember here when we made the PDP-5, it was built to do a control job. It was built in lieu of a specialized controller for building a sample data system, because we looked at the controller problem, and it turned out that we needed a memory to store the control variables in, or it was actually an alarm scanner. A memory to store the alarm values in, and it also required a fair amount of control to sequence through to sequence and find and do that alarm scanning process. So we immediately, since we were all computer people, we said, oh, the cheapest way to build a computer is with or the cheapest way to build a controller is with a computer, because we know all you have to do is to build a computer, you first start with a memory, and then you add a little bit, and if you look at our machines, you've got a computer, and the 5 had an MAN and memory address and memory buffer register, which you need for memory, and it had one other register that could do addition, an accumulator, and then 2 other bits, an interrupt bit and a run bit. So it had, and then the link. So it was 15 bits of memory outside the memory itself. Program counter was put in the memory, and we used that. In fact, we built the D to A converter into the accumulator to do that, so it had an A to D instruction built into the machine. Didn't add any registers. That's the time where registers cost money, and we'd go out and do a control application, and people had hardwired controllers, and they said, "How can you do all of that?" And we said, "By not having sequential control, you get this tremendous flexibility because you're storing the control in memory." And the semiconductor industry is realizing that today, and that's why the emphasis on making, every semiconductor company is making a microprocessor or so, because they find out that's the cheapest way to do control. Flip-flops, sequential circuits just aren't good. It's just not a very good way to do control. You can do a lot of damage. You can do a lot of damage with programs. I guess it's not clear. You can do it faster. You can do a given job faster with sequential circuits, or rather runtime, but a logic designer can't create too many problems with sequential circuits because it takes a long time to do a sequential circuit design. Programmers can create probably more wrong answers than logic designers. But the fact that it's totally sequential, program is totally sequential, gets rid of a lot of the problems that a bad logic design can do. And as a person who works with and does a lot of I don't do any logic design now, but I look at a lot of logic design. The day we can get rid of a lot of the logic design, I think, is going to be machines are going to run a lot more reliably. There's just something very nice about the program aspects here of sequentializing a lot of the control, as opposed to having to make a sequential circuit, which has a lot of inherent parallelism in it that leads to many races and all kinds of hazards that we just haven't been able to at least cope with from a discipline standpoint. So now if we look at some of the other parts of technology, you look at the disk price. This is, here we've got, again, a log scale. This is two curves. This is price in dollars per megabyte of storage. And again, a number that's about 41%, so you can use the same factor of 2. And the price has come down about a factor of 2 per year, per 2 years, over the life of, starting with the disk. These are large disk files, starting with the IBM 1311, going out to the 3330s. The capacities here have gone up, notice, by about a factor, a little bit bigger factor than this has. So it turns out the mechanism, if you look at why that's happened, the mechanism themselves has remained relatively constant. That is, a disk file, they all sell for about $25,000. These happen to all sell for about $25,000. In fact, these are sold for a little, the prices have gone up a little bit in that. And that's because, going back to all those learning curves, what's in it is a bunch of sheet metal, power supplies, motors, and none of that stuff has changed. And so we're out at the, we've made several billion motors, and another 100,000 or so here isn't going to drive the price down very much. So you're sitting there, an established technology, established motor technology, and you aren't able to do very much with the price. And where this has all come about is in magnetic recording density, so that the cost has remained constant, and you've gotten performance out of just packing more on tracks, making better track servos and higher densities in the recording. So they've changed too, but not as rapidly as the semiconductor industry. So you can look at here, now let's look at it a couple of ways. I've shown time functions, and I've shown unit functions. Namely, this first curve where we compared it with the automobile, it had the ith unit to the b, where this was a technology progress function, and that was like 2.5. And all these other things have been with respect to time. And there, the technology of the tth unit is equal to some constant times e to the t. And that's a wild function too, and again an exponential. Turns out these two are identical if you build at an exponential rate. If you're always building more each year as a constant percentage of the previous year, then then these two turn out to be the same function, and you can look at it with respect to time instead of with respect to the number of units, which is a lot easier because you'll never get any reasonable unit counts out of anywhere anyway. You've got to look at what's the price you're paying today, and you know that, and you can do these comparisons. So I tend to use only time because it's the difficulty of these unit numbers, but they are the same. So let's look at the components. Here, semiconductors have improved at like 60 to 80% per year. Now that's a real wild function compared to these mere 30 or 40% improvements. And in fact, the semiconductor memory has improved at 100% a year. There is one, if you look at the bipolar RAM technology, starting in 1962 was about the first bit. In 1964, there was let's see, a 4-bit, a 4-bit, and 66 there was a 16-bit memory on a single chip. So again, it's like the disk. The chip is kind of given. That's a fixed kind of cost size thing, and the technology has been to put more and more on that chip. And looking at that in aggregate, then that function is 2 to the t, where t is measured since 1962. So if by that token, we're sitting here at 74, and it's been 12 years since 62, and so we're sitting here 2 to the 12th bits on a single chip, and which is about where we are. 4,000 bits on a single substrate in the order of about 150 mils by 150 mils. So that's a really wild function. That's a scary one because nothing ever you can't double. I don't know who that famous biblical story or about the grains. It doesn't go on very long. You reach limits there, but you can see it go for maybe another 5 or 6 years, and then people begin to worry about optical limits and things like that. Well, people are already worrying about optical limits, and it looks like there are ways around some of these. And then you go to then there's an electron beam technology for getting higher densities, but you're really, that's still going to go for a while. I think it may slow down a little bit, but there's a long way to go in terms of densities there. So this is really the wild function. Everything else is pretty tame by comparison. Disks, I think they've changed about 35% per year overall. Systems, 25 to 35%. So if you take the whole thing as an aggregate, it turns out to be about that. Tape, that hasn't changed very much. Again, because of this reliance on motors and sort of fixed technologies. Cabinets and power supplies, not very much, 0 to 10%, because people have been bending sheet metal for about, well, probably several thousand years, or at least molding metal, and that that we've learned, even though we learn something about that every day, it's far down on learning here. Core memories, they've changed in the order of about 30% per year. So that changes. And it turns out the thing that's changed core recently has been the threat these guys are going to wipe them out. So a little bit of competition. They've always had that threat, though. No one's really ever gotten very close. But the semiconductors have a history of this 2 to the t function. I'm worried there that they're really going to do it. And it looks kind of inevitable as far as I'm concerned. So if you look at kind of, I've got about 3 curves here. Machine population, totals, we're out in about 100,000 machines. The Mini has grown faster than the general purpose, which is kind of slacked off here. You look at percentage of system in over time. You're sitting here. The processor has gone from like in 55 being the dominant part of the machine down to like 15% of the machine now. Memory is going up in terms of the percentage cost. Peripherals have gone up and are staying relatively constant. But terminals have come up and will tend to be much more of the dominant part of the cost. So it's hard in mixing. You really have got to mix these two. Processors have really come down as being a significant part of the machine cost. This one, that's the software technology. Turns out to be lines of code that have been written, and we're up to about 100 million lines of code that have been written now, and I think that's probably a little bit small in terms of the really number. In terms of sort of substantiating this thing, I'll put this one on anyway, and it's a little bit hard to follow, but let me give you some ways at least that we use to look at this, and that is that we've got a computer price, again our log scale, performance, which is processor accesses per second to the memory for instructions and data. And if you look at the PDP-5, PDP-8 technology, we started here with the CDC machine in terms of being here at a given performance. We slid down increased the performance decreased the performance a little bit, decreased the price, and then we moved over to the PDP-8 technology in 65, and then moved down at a constant performance down to the current machine. These are all about 1.5 to 1 microsecond. So the technology, we're staying constant performance and we're decreasing price all the time. So the mini computer tends to move in this direction, and the other machine tends to, and other machines tend to move in this direction on this curve. You're trying to spend the same amount of money, do significantly more. These lines I've drawn are constant increasing, constant price performance. So the rules of this board game essentially are, when you move, you got to move down and these are factors of 4. So if you make this, that's a 4-year interval, if you assume 41%, then as you move, you've got to move down one of these lines in 4 years. And in fact, here's a 70 to 74, and that's roughly not quite a whole line. And here's 71 to 68. That's 5 years, and it's not quite a whole. That's 5 years and about one line. So constant performance this way, I'm sorry, constant cost, constant performance, and then we move around with respect to time. Time being an important parameter in the measurement. There's another law that's never been proven with respect to computers, and that is that you as you compare two machines of a given time, then this goes up. This has to be at, let's see, I guess a slope like this, namely that performance is equal to the cost of the machine squared. So at a given point in time, as you double the price of the machine, you must go up by a factor of 4 in performance. That's a phenomenon known as Grosch's law, in which he formulated it to say that the more money you put into a computer, you should get four times or you double the price, you should quadruple the performance. And there's been lots of there's been some empirical work to decide what that is, and to a certain extent that's a pricing problem too, because people may price according to that law too. But in general, yeah, there's a point that we can put more and more in a machine and get more out until it reaches this point of diminishing returns, and or as you hit a limit in the technology, you just can't build the machine, and that's what's happening in some of these very large machines. That everything you can put in because of the generality pays. But the trouble is, something hits them before they can get all that junk in. That is light, speed of light, you know, the power supply, all these dumb things that have no business of going after them. But with the large machines, it's usually those mechanical considerations, physical considerations that limit one before you get all of the stuff in that you really would like to put in. In terms of DEC's own machines, here's sort of what I've observed here. We've got really kind of we better not tell anybody. We've got kind of a conglomerate of people and groups. We've got the PDP-8 here, which is on this sort of minimum. Their goal is to have the lowest price computer at any time. That's clearly what their business is, and they follow those curves. The PDP 479, that series has actually been much more of a constant performance, and in fact, if you look at the average PDP, the 18-bit machine sold, that turns out to be a very constant price, and that the average system there has been about $100,000 ever since the machine was developed. The PDP 610 series, that's the 36-bit large machine, that machine price has gone up, and the average price has gone up considerably. And so as it gets new things, they are on this track of putting more and more in a box and selling it for more and more with a constant set of users. The 11 has come in here in this low end, and it's sort of gone up, and it's trying to cover some of this. And we have at DEC what is known as the gap there, which is we don't have a machine. There's a machine price performance area that we don't really cover. So look, that's all I had in terms of anything that's the way of formal. You've looked at a lot of data, I hope, and at least this is the perspective that I have in terms of what it is that generates generates machines. So we're looking at think of it as a process, and all these curves, we're looking at the output of that process. And that's kind of the way I think of machines. And if you have some questions, why, let's fire.
It seems like all machines are, you have these generations, first, second, third, fourth generation machines, and it all has to do with the hardware. Has there ever been a, consensus on generations of architecture of machines, or has it just been a gradual thing in architecture?
Well, each in terms of operating systems, there's been a similar kind of generation of operating systems. That is something where you can identify a technique that's made the way you build operating systems change. Same way with compilers. That each component tends to have a generation onto itself where there's been some specific input where you can identify a totally different way of doing things.
People ever feel there'll be a great breakthrough in any type of architecture? The architecture might make things completely different.
Well, I guess I think that the technology now is driving to make a bunch of changes in architecture, things that you would never have done before you do now. Yeah, where it's now cheaper to put a computer as a controller as opposed to building a special hardwired controller. So that, in fact, putting lots of computers in a system, in effect, lots of program counters to do a job, that tends to be a kind of evolutionary change that's going on. And if you look in the evolution of control in a computer, that we started out with the very first machine of you draw, I think textbooks still do it. What's a computer got? Well, it's got whatever those 5 boxes are. Input, output, memory, control, arithmetic element, and you have this big control that sort of goes everywhere and does everything. And that's a recursive structure, it turns out, that, well, you got memory, fine, that's got its own control that operates totally independently. The input, that's got its own control. And we've pushed control out in every part, made them substantially more complex, made them so that they can diagnose themselves, they can operate more autonomously. And it's an evolution. I like to think it's an evolution very much like an intelligent, if you go back to life itself, that whole business of centering, of taking the intelligence and moving it out with the function that it has to control. I mean, that's pretty much the way humans have evolved, or that very early animal life had not had control, highly centralized control, and now people are pretty much built with tremendous amount of decentralization. And I think that applies again recursively as you put a computer into a system. We'll put lots of computers in a system. You want to do, there's a place for the desk calculator kind of thing. There's a place for coupling and decoupling, and that puts a tremendous pressure on communications, just like there's a pressure on human organization communication. All of these increased number of machines is putting an increase on inter-machine communications. Otherwise, we've got this funny inverted society in which we got all these nifty machines that are doing everything for us. What are the people doing? Well, they're just carrying input from one to the other. And it's kind of getting boring. We'd like to be able to transmit that from, among machines a lot easier. Yeah.
On your growth curve for the 8 series, you show an advancement roughly every 4 years. And with the 8A being the latest,
yeah.
What's the next step?
Well, the 8, remember the way the 5 was built in the first place, it had like only 15 bits in it. With the 8, it turns out an 8 is about the simple. It's optimized to a 4,000 word memory. It turns out it still beats everything on the block as far as the microprocessors are concerned. It's the most efficient machine that we've been able to find at that level, and it's very easy to put one of those things on a chip. It's so trivial compared to these other machines that are being put on a chip. It turns out to be a nice one to do that way. It's got more software, and the neat thing is that software is there's no way I don't have any way to look at the software in this way with a good indicator, but software is sort of like a vintage wine that it reaches a maturity over a long time. It just takes quite a lot of use before it's stable and people have settled into using it.
Would you expect your 8 series then to sort of flatten out on your cost curve with the 8A, or?
No, I see it continuing to come down in price, because there's no reason that it's going to flatten out, because just alone that it's going to parallel it's got to parallel all the other curves, because it's got less bits in it than a 16-bit machine, for example. And so you've got that difference there, and you look at the price of a machine, and it turns out to be, you just count the number of bits in it, and you want to look at the price of the processor, you count the number of bits in, the area of it, or the bits or the area of a chip, and that's all related to price. And the 8, no matter how you slice it, the 8 is about the cheapest machine that you can build.
But do you see anything, sir, beyond the 8?
In what way?
Well, as far as like entering your 4th generation.
Oh yeah, in terms of as the densities, as the semiconductor densities increase, well, you can make the same statements about there's a right time to put an 11 on a chip or a couple of chips or something like that, because as long as it's economical to do that, you've got to get the volume there in those chips to make sure it's the right. It's right from a cost standpoint, because if you lead too far in the technology, it just won't quite fit, and you'll never get the yields, and the prices will be higher than if you don't do it that way.
In other words, would you say that software will eventually be, like we've been told, that software is starting possibly to be the 4th generation of computers?
Oh, I don't see that software is a 4th. I don't look at that as a. I'd prefer to say software turns out to be the dominant cost of a system, and you worry about software really more than machine costs. That number, that percentage at any given level of system is becoming a really dominant cost.